Welcome back to Derivatives and Risk Education. In the previous video, we built a multi-period binomial tree for option pricing. But behind every tree, there is a probability space. In this new series, we'll build that space from the ground up. We'll start in this video with finite probability spaces. Then in future videos, we will cover random variables, expectations, conditional expectations, martingales and Markov processes. These are the mathematical foundations of discrete-time finance, and they'll prepare us for continuous time models later on. So let's begin with the basics, the finite probability space. Suppose we toss a coin 3 times. We can build a binomial tree for this, with the first, second and third toss. We see on the right that the set of all possible outcomes after 3 tosses is as shown here. Note that each outcome is a full path, a sequence of 3 tosses. This set of all possible outcomes is called the sample space, and we'll denote it by the Greek letter omega. Now, let's assign probabilities. Suppose the probability of heads is p, and the probability of tails is q, which equals 1 minus p. We assume the tosses are independent, so the probability of each path is the product of the probabilities of the steps. For example, the probability of the outcome of 3 heads, HHH, is p times p times p, which simplifies to p cubed. Similarly, the probability of HTT is p times q squared, and the probability of THT is q times q, so p q squared. Now, an event is any subset of the sample space. For example, the event first toss is heads. We see this displayed in the tree and then also in the table. So the event first toss is heads includes all outcomes that start with H. HHH, HHT, HTH, and HTT. To find the probability of this event, we sum the probabilities of these 4 outcomes. That gives us p cubed plus p squared q plus again p squared q plus p q squared. Then we can first take out a factor of p and then further factorize as p times p plus q squared. Since p plus q equals 1, we get p times 1 squared, which just equals p. And this is of course the probability of getting heads on the first toss. So the maths agrees with our intuition, but we should always verify. Let's now define a finite probability space formally. It consists of a sample space omega, which is a non-empty finite set, and probability measure p, which assigns a number between 0 and 1 to each outcome little omega in the sample space big omega. These numbers must add up to 1, which we can write like this using sum notation. An event is any subset of the sample space omega, and its probability is the sum of the probabilities of its outcomes, which we can write like this. Probability of an event A is the sum of the probabilities of each outcome little omega that is in the event A. If the probability of an event is 0, it's impossible, and if the probability is 1, it's certain. And if 2 events are disjoint, meaning they don't overlap, then the probability of their union is the sum of their probabilities. This structure that we looked at today underpins everything in binomial asset pricing. Each path in the tree is an outcome in the sample space omega. Each event, like the stock ends above the strike price, is a subset of the sample space. Pricing options means computing expected payoffs over this space. So, to recap, we defined the sample space omega for 3 coin tosses. assigned probabilities to each outcome, and showed how to compute the probability of an event by summing over its outcomes. We gave formal definitions of the sample space and events, and showed the connection to option pricing. Altogether, this gives us a foundation for modeling uncertainty in discrete time. But this was just a start. In the next video, we'll define random variables on this space, functions that assign numerical values to outcomes. We'll use them to represent payoffs, compute expectations, and lay the groundwork for pricing. Thanks for watching. Don't forget to like and subscribe.